Lesson: Core concepts: machine learning, deep learning, and neural networks. Machine learning, deep learning, and neural networks are pivotal components in the field of artificial intelligence, each interrelated yet distinct in their capabilities and applications. Understanding these core concepts is essential for professionals aiming to become proficient AI architects. Machine learning, at its foundation, involves the development of algorithms that enable computers to learn from and make decisions based on data. This capability is crucial in addressing complex problems across various industries, from healthcare to finance, where traditional programming methods fall short. A practical understanding of machine learning begins with grasping its types: supervised, unsupervised, and reinforcement learning. Supervised learning involves training a model on a labeled dataset where the input-output pairs guide the learning process. For instance, in a real-world scenario, a company might use supervised learning to predict customer churn by training a model on historical customer data where the outcome is known. Tools such as scikit-learn, a powerful Python library, offer extensive functionality for implementing supervised learning algorithms like linear regression and decision trees, making it accessible for practitioners to develop predictive models efficiently. Unsupervised learning, on the other hand, deals with unlabeled data, where the algorithm seeks to identify patterns or groupings within the data. Clustering techniques, such as k-means and hierarchical clustering, are instrumental in this domain. For example, marketers use clustering to segment customers based on purchasing behavior, enabling targeted marketing strategies. Frameworks like TensorFlow and PyTorch provide robust libraries for implementing unsupervised learning models, allowing professionals to leverage neural network architectures for complex pattern recognition tasks. Reinforcement learning is a dynamic approach where agents learn to make decisions by interacting with an environment to maximize cumulative rewards. This method is particularly effective in scenarios where decision-making involves a sequence of actions, such as robotics and autonomous driving. Reinforcement learning frameworks like OpenAI Gym offer a suite of environments for testing algorithms, providing a practical platform for developing and benchmarking reinforcement learning models. The evolution from machine learning to deep learning marks a significant advancement, characterized by the use of neural networks with multiple layers, known as deep neural networks. Deep learning has revolutionized fields such as computer vision and natural language processing by achieving unprecedented levels of accuracy. A quintessential application is image recognition, where deep learning models like convolutional neural networks are employed to classify images with high precision. The availability of pre-trained models in libraries such as Keras, which operates on top of TensorFlow, simplifies the deployment of deep learning applications, even for those with limited domain expertise. Neural networks, the backbone of deep learning, mimic the human brain's structure, comprising interconnected nodes or neurons that process information. Understanding neural networks involves comprehending their architecture, including input, hidden, and output layers. A classic example is the use of recurrent neural networks in sequence prediction tasks like language modeling, where the network's ability to maintain a memory of previous inputs enhances its predictive performance. PyTorch's dynamic computation graph facilitates the implementation of RNNs, offering flexibility and ease of use for researchers and developers. A critical aspect of mastering these technologies is the ability to address real-world challenges, such as overfitting, data quality, and model interpretability. Overfitting, where a model performs well on training data but poorly on unseen data, is a common pitfall in machine learning. Techniques like cross-validation and regularization help mitigate this issue, ensuring models generalize well to new data. Cross-validation, available in scikit-learn, partitions the dataset into training and validation sets multiple times, providing a robust evaluation of model performance. Data quality is paramount, as the efficacy of machine learning models heavily relies on the quality and quantity of data. Data preprocessing steps, including normalization, handling missing values, and feature engineering, are crucial in preparing data for machine learning tasks. Practical tools like pandas and NumPy facilitate efficient data manipulation and cleaning, enabling professionals to pre-process large data sets effectively. Model interpretability remains a significant concern, particularly in domains like healthcare, where understanding model decisions is crucial. Techniques such as SHAP provide insights into model predictions, allowing practitioners to explain the impact of each feature on the output. This transparency is vital for building trust in AI systems, especially in sensitive applications. Case studies highlight the transformative potential of these technologies. In healthcare, deep learning models have been deployed to analyze medical images, assisting radiologists in early disease detection. For instance, a study demonstrated that a deep learning model outperformed human radiologists in diagnosing pneumonia from chest X-rays, showcasing the model's potential to enhance diagnostic accuracy. Similarly, in finance, machine learning algorithms are employed for credit scoring, fraud detection, and algorithmic trading, where their ability to process vast amounts of data in real time provides a competitive edge. The integration of these technologies into business processes necessitates a strategic approach, where understanding the problem domain, selecting appropriate models, and evaluating their impact are critical steps. Tools like MLflow streamline the machine learning lifecycle, from experimentation to deployment, enabling seamless collaboration and tracking of model performance in production environments. In conclusion, mastering the core concepts of machine learning, deep learning, and neural networks is imperative for professionals aspiring to excel in AI architecture. By leveraging practical tools and frameworks, practitioners can address real-world challenges, deploy effective solutions, and drive innovation across industries. As the field of artificial intelligence continues to evolve, staying abreast of advancements and continuously honing one's skills will be key to navigating the complexities and opportunities it presents.